For the next part, we look at calibration curves. A calibration curve is a graph that shows how one quantity varies with another quantity. When a physical quantity measured is represented by one axis of the graph, while the other axis is represented by the reading on the measuring instrument, it allows the sensitivity of the instrument to be deduced. The gradient of the graph is a measure of the sensitivity of the measuring instrument. An instrument is sensitive if a small change in input results in a large change in output. Take, for example, the volume of fuel remaining inside the fuel tank of a vehicle that is indicated by the deflection of the fuel gauge needle. When the volume of fuel is increasing, the needle will deflect in this direction, whereas when the volume of fuel is decreasing, the needle will deflect in the opposite direction. In figure 1, the angle of deflection theta of the fuel gauge needle is plotted against the volume V of the fuel remaining inside the fuel tank. The output is the angle of deflection of the needle. The input is the volume of fuel remaining. If we have an equation y equals to a divided by b, then we can say that y is directly proportional to a, such that when y increases, a also increases. On the other hand, we can say that y is inversely proportional to b, such that when y increases, b decreases. In figure 1, the gradient of the graph is equals to delta theta over delta v. The angular deflection is the output, whereas the volume change is the input. Looking at the graph right now, we see that the gradient is increasing. An increasing gradient causes a large change in the angle, but a small change in the volume. We have a case where a small change in volume results in a large change in the angle. In other words, a small change in input results in a large change in the output. Therefore, we can say that as the gradient of the graph increases, the sensitivity increases. If we have the same graph shape, but the graph axes were reversed, as in figure 2, we will say that the gradient is equals to delta V over delta theta. The volume change is the input, whereas the angular deflection is the output. Looking at the graph again, we see that the gradient is increasing. An increasing gradient causes a large change in the volume, but a small change in the angle. We have a case where a large change in volume results in a small change in the angle. In other words, a large change in the input results in a small change in the output. Therefore, we say now, as the gradient increases, the sensitivity decreases. Bear in mind right now, although the graph shape is the same, they're telling us different things for the sensitivity. Figure 1 says that the sensitivity is increasing, whereas figure 2 tells us that the sensitivity is decreasing. It will really depend on how the graph is given. Apart from looking at the gradient of the graph to determine sensitivity, sensitivity can also be determined by looking at the interval changes on the graph, specifically the interval change in the output for every equal interval change of the input. For every equal interval change in the input, if there is an increasing interval change in the output, then the sensitivity is increasing. Take, for example, the graph here. For every equal interval change in the input, notice that there is an increasing interval change in the output. Therefore, we would say that the sensitivity is increasing. Conversely, for every equal interval change in the input, if there's a decreasing interval change in the output, then the sensitivity is decreasing.